Hi, everybody. Obviously, I'm not there today, so I hope that you can get everything you need from this lesson from the PowerPoint and everything that we'll go over again when I'm back on Friday. So today we are starting a new part of this unit. We've just finished atomic theory and history and types of models. So now we're actually going to get into why that's important in terms of the periodic table. The first man you need to know is Dmitry Mendeleev, or Dmitry Mendeleev. His name is pronounced both ways, and he's considered the father of the periodic table. He actually formed our first periodic table, and you'll see in the next couple of slides. We've updated it since him. All you really need to know about him is he invented the periodic table. He is a crazy Russian man who took a lot of credit for other people's work, so people didn't really like to deal with him very much. So he organized the elements by properties, and in doing so, he saw that elements also were lining up in terms of their atomic mass. So if you remember, atomic mass is neutrons and protons put together. And from this, he could see a pattern arising where you have increasing atomic mass with certain changes in properties, in equivalent increases in mass would lead to elements lining up in which they started to have the same properties. And this actually led him to predict the existence of some elements that weren't discovered at the time. Some of them were gallium and germanium. He knew that there was a spot left for elements to go there. And what he actually did was he called them eka aluminum and eka silicon, which means under. Like similar to under aluminum, under silicon. And this picture is to show kind of what his original periodic table looked like. So it had the letters in there, had their masses in there, and obviously it's not anything of what we look at as a periodic table now, but this was the start. And if you can look at certain places like between Hg, Mercury, and gold, Au, you'll actually see there were some spaces left. And he left those spaces strategically to have a safety net in case new elements were discovered. He also left question marks because he knew something had to fit into certain places. So he actually was very, very, very intelligent when it came to putting together the periodic table in terms of atomic mass. And here is just a list of some of the properties and everything that he could see coming up with the elements that he predicted. So on here you can see, like I mentioned earlier, gallium and germanium, just as two of them. And what he predicted the properties to be in the middle column versus what the actual properties were once these elements were found in the right column. And you can see how similar, like the masses are, how similar the densities are, and everything like that. So a couple things you do need to know about the periodic table before I move on to the next part is that now we actually have a different way of looking at the periodic table. We learned over time that mass was not as reliable in terms of setting up a pattern as other aspects were discovered. So we started to see that certain elements, if we put them in the place in terms of their atomic mass where they would fit, they actually did not show the same properties. So there started to be a couple different exceptions to that rule. So we had a scientist whose last name was Moseley, and he actually set up the periodic table in the way that we look at it now with increasing atomic number. So every element increased by one proton from left to right, increasing the atomic number, changing the element, and thus changing the properties. We have this law called the periodic law, and all that states is that atoms in the same column will have very similar properties. Atoms across a period will range in properties. You'll see those properties vary a little bit more. So what you need to get from that is that Dmitry Mendeleev created the first periodic table with increasing atomic mass, but our current periodic table is in increasing atomic number. So now that we know a little bit about the periodic table, we can look at it and the specific parts of the periodic table. And the first thing we need to look at is the major sections of the periodic table, which are the types of elements we've got there. And those are labeled as metals, nonmetals, and metalloids. So here you can kind of see the different colors to separate your metals, nonmetals, and metalloids. If you look at this kind of lavender purple color, these would be where your metals are located. So about 80% of your periodic table is considered a metal. The two at the bottom as well that are in the blue shade, so you can't really see them as well, are also considered metals. If you look on the stair step where you see the light blue, these are our metalloids or semi-metals. And then the yellows are our non-metals. And here just shows where each of those are located. And a lot of periodic tables do really good at putting in that stair step for you. However, some of them don't. So if I ever give you one and you'd like to write that in, that's perfectly fine. Just don't do that on my reference packets. So we know where they're located. Now we can talk about some properties of metals, metalloids, and nonmetals. So metals, which like I said are 80% of the periodic table. You guys know lots of metals. We listed them earlier when we talked about cations and anions. Some of their descriptive properties are that they're malleable, lustrous, ductile, good conductors of heat and electricity. Now, a couple things with these. Malleability, if you do not know, malleability means hammered into sheets. So you can hammer metals into sheets without changing the integrity or breaking apart the metal. Lustrous just means they have a shine. Ductile means they can be stretched into wires. This is why we like to use copper wiring a lot, because it's a really good conductor of electricity and it's easy to stretch into wires. And last, they're good conductors of heat and electricity. We've talked a lot about how you never want to be stirring something with boiling water with a metal spoon and leave it in there because it gets really, really hot. That's because it's a good conductor of heat. If you remember, that means they also have a very low specific heat. Nonmetals is the second largest portion of the periodic table. Those were on the right side, and they also included hydrogen. And these are normally gases or brittle solids. So an example of a brittle solid here is carbon. Metals are almost entirely solid except for mercury. So nonmetals are normally gases, sometimes brittle solids, and one liquid is bromine. At room temperature, they are poor conductors of heat and electricity. So we don't use these to conduct heat and electricity. And if you think about it this way, gases wouldn't be able to as much because there's not as much structure there. And then the last is metalloids, so the ones on the stair step, or your semi-metals. They are dull, brittle semiconductors. So these are really good for a lot of internal wiring because they don't get so hot that they melt or catch fire. So for example, here it says they're used in computer chips because that way it'll keep them from breaking down or melting, but it also still allows them to conduct high amounts of electricity. So a little bit more about these classifications. So the zigzag line, like I said, that runs between groups 13 and 16, those are your metalloids. And when we look at those, we need to know that they have properties of both metals and nonmetals. Those properties can change a little bit when it comes to bonding and what they're bound to. So I think an example in your notes is that silicon is like a really bad conductor, but if you partner it with boron, I think, which is another semi-metal, it becomes a very good conductor. Just look at that example in your notes. I'm pretty sure that's it. And here, just again, repeating some of the things that we talked about with metals. Here adds a little bit more that metals lose electrons and form positively charged ions. Remember, those are called cations. And the vast majority of the known elements are metals, and that's because they make up most of the periodic table. And then a little bit more about your nonmetals. They tend to gain electrons in reactions with metals to form negatively charged ions, or your anions. Now, sometimes they also share electrons. And when they share electrons, they tend to do that with other nonmetals. So we've gone through our specific larger groups of the periodic table. Now we can talk about our families, or our specific columns or groups of the periodic table. Here's a good time to point this out, as you can see them, or see this periodic table on the screen. If you see a column, that is called a group. And if you see a row, so horizontal, that is called a period. So that way you can tell the difference. When I say group, I mean the vertical columns. So it looks like we're going to look at group 1A first, and these are called the alkali metals. Make sure you call it alkali and not alkaline, because those are two different groups on the periodic table. So your alkali metals are from lithium to francium, group 1A, and we know that they tend to give up their one valence electron, which would give them a +1 charge. So they would be a +1 cation. Hydrogen is put in this group because it has one valence electron, but it is not a metal. It is still considered a nonmetal. And then compounds of alkali metals are common in nature and daily life. So a lot of our salts that we consume every day tend to contain an alkali metal. Our next group is 2A, and this is alkaline earth metals. So this is why you can't say alkaline for group 1. So these are alkaline earth metals. And they contain beryllium to radium, and all of these will react with nonmetals. They have 2 valence electrons, which means they will give them up. And this slide is actually incorrect. It says that it will readily react with nonmetals to give ions with a -2 charge. That -2 charge would be on your nonmetal. So actually these would have +2 charges. So beryllium through radium would gain a +2 charge because they lose 2 electrons. Now we're going to skip the short section in the middle because those are our transition metals, and they are very tricky. We don't actually look at their valence electrons to know how they bond. There are just some memorization that you're going to have to do there. So we're going to jump all the way over to group 17 or 7A, because groups 1A, 2A, 7A, and 8A have very specific names that go with their group. So 17 or 7A is called the halogens. It's fluorine down to astatine, but we tend to you really go through iodine. And these like to react with a metal, so they like to gain that electron from a metal and form a -1 cation. And here just shows a couple things about these gases. So we've got fluorine, tells its boiling point, atomic mass, all the way through astatine. Now, something you will see here, if you look in the third section of this chart, you'll see that I wrote their atomic symbol. However, I wrote it with a little 2 in the corner. These 2s, so F2, Cl2, Br2, and I2, that means you have 2 Fs bound together, 2 Cls bound together, 2 Brs bound together, and 2 Is bound together. This is what we call a diatomic element. If you remember me talking about this on review day for Unit 2, and we said that they could be considered a compound or an element, this is why. These are 4 of the 7 that we will look at as diatomic elements. Our next group is the noble gases, which is group 18. And this is from helium down to radon. These are called monatomic atoms. So when we hear this word, think of the prefix mono, meaning one, and atomic atom. So this is one atom. What that means is they do not bind to anything else. They like to stay on their own. Once you get down to like xenon, then they may start reacting with stuff, but it's because they're so big, it can attach to them and it wouldn't know. So they are very unreactive gases at room temperature and pressure. They are also called inert gases. So the word inert means inactive. And now you'll see the names of these groups, but what we will tend to call them for groups 3 through 6. So the first one we're going to start with is 16 or 6A. Here they're called the chalcogens, but we also call them the oxygen family. So with these, it's oxygen down to polonium. And a couple things you'll want to know about this is they have an S2P4 configuration. That means nothing to you right now, and that is completely fine. This is something that we will cover tomorrow in detail because this is one of the bigger parts of your final exam. So their chemistry is dominated by three oxidation states. -2 is the one we tend to get here, and this is when like oxygen or sulfur gain 2 electrons to get that outer octet. It shows on here that +6, where all valence electrons are lost. However, we don't really like to do that, we know, because that's a value we'd rather not have. And then +4, where only 4 electrons are lost, and it gives a full s orbital. So again, a lot of this, when it talks about configurations and subshells and all that stuff, I know that this is not common knowledge to you. I know that this is probably going to go over your head, but this is something, if I can explain it a little bit today, then when I get into class tomorrow, maybe I can make those connections that will kind of set it in stone. Okay, the next one is our nitrogen family, group 15. And here talks a little bit more about their electrons. You need to know it's normally a -3 charge. So we usually deal with number 1 here for a -3 charge. And 14 is your carbon family, or 4A. And these straddle the diagonal line that divides nonmetals and metals. We've got carbon, which is a nonmetal, silicon and germanium, which are semi-metals, and tin and lead, which are definitely metals. Talks a little bit about their configuration as well, but we don't tend to use a charge here on these. I will say this, though, for number 2 and 3 at the bottom, where it says +4 and +2, those are the charges that tend to go on lead and tin when they react with a nonmetal. And then 13 is the boron family. Group 13 most of them are metals except for boron. Boron is the only semi-metal in this group. And these are highly reactive, and they like to form compounds with oxygen a lot. And again, here's something about their valence electrons. You don't really need to worry about that today. The last 2 little sections we need to look at, just so you know what they are. At the bottom are 2 little columns, 2 little rows that actually fit into the periodic table. If you can see LA and you look in the rows starting with scandium, I think, and look 3 down, you should see LA. It's the same one. So these 2 rows come out of the inside of the periodic table. We take them out so that we can make it look more confined. So the LA group is called the lanthanide series because the atom is lanthanum. And these are normally, I think most of them are actually synthetically made, but they are what we call an inner transition metal because they're within the transition metals. And the next one is the actinide series. So this would be AC. And same for these, they're mostly synthetic inner transition metals. So if you look here, I know that this periodic table is really sloppy, so don't really pay attention to anything except for the colored sections just to know what they mean. Let me get back. So this section in the middle, your little short stack in the middle of your towers, are your transition metals. These are the ones that can have random charges. And that's because they transition a lot easier. And then your inner transition metals, because we have them within your transition metals. So if you look in the transition metals section, you'll see a little asterisk and a little omega sign. Well, those symbolize where your lanthanide and actinide series actually would be in your periodic table. And then the last little bit we have to talk about today is electron configurations, just starting it, showing you where some locations are on the periodic table that will help you when I get back on Friday. So if you look at this periodic table, we've got the shape, but now we've put weird things in here, like we don't have elements anymore. Your periodic table is broken up specifically to where your orbitals can be in place. So if you look here, I've got like 1s through 7s, 3d to 6d, 2p to 6p, and then 4f and 5f down at the bottom. Okay, so if we look at the next picture, I'll be able to explain it a little bit better. Here we go. So columns 1 and 2, groups 1 and 2 are considered our s groups. And if you think about it this way, an s orbital can only hold 2 electrons. Well, as you go from like lithium to beryllium, that would be gaining 1 electron. So lithium has 1, beryllium has 2, only holds 2 electrons. That's why it's in an s orbital. Then you need to jump across the d orbital over to the other side, and it would be your p orbitals. You'll see I separated out the s at the top because helium only holds 1 other electron, so it only holds 2, causing it to not be considered a p orbital. So if you look in our p orbital section, and if you think back, p orbitals, there are 3 of them. Each of them can hold 2 electrons, so altogether it can hold 6 electrons in 1 p orbital. Well, if we stay in one row and we work our way across, starting at the furthest section of the p square here, we've got 1, 2, 3, 4, 5, 6 elements that make up 1 p orbital. 6 elements, 6 electrons. Okay, this is how we're getting some of these numbers here. Then the short stack in the middle, we go back to the d orbital. D orbital, if you count all the way across, d orbital can hold 10 electrons. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 elements, 10 electrons. And then down at the very bottom, the f orbital, which you will not have to use for configurations, but it is good to know. There are 14 elements there, 14 blocks, because it can hold 14 electrons. So this slide just shows a little bit about metallic and non-metallic characters. As you go more to the bottom left of the periodic table, you are getting very, very, very metallic. So cesium and francium. Top right, you are getting much more non-metallic. And then our last couple slides, we have our own oxidation states. What oxidation states means is charge. So we're looking at the charges on these elements. Remember, group 1A are always +1. You see I just have that little plus sign up here. I don't have, I only have this little plus sign, which means +1. And then in 2A, they're all +2s. 3A, I've got a +3 on aluminum because we know that's a metal. 5A, I've got my -3 on my nitrogen. 6A, they're all -2s, and 7A, they're all -1s. Remember, your noble gases do not have a charge, and your 4A's tend to do covalent bonding instead. And then our last slide here just shows them again a little bit more separated out in color-wise. And then in your transition metals, we actually have 2. And these are 2 you actually want to write down and remember because they have multiple charges, but the ones given on this chart show the normal one that you receive, the normal ion that will form from these. Okay, so that's the end of the lesson. I hope this kind of helped you understand kind of what's going on in the notes, but this shouldn't have been too hard for you. If you've taken physical science or any science class ever, you've seen a periodic table before. It's very basic stuff. We will go into detail with the electron configurations and reviewing this stuff tomorrow. So please work hard to answer the questions on the homework as much as you can, and to make sure you read over these notes and have any questions ready for me on Friday.